All right, so just as a quick reminder, last time we finished by talking about the potential energy due to the elastic, or the potential energy associated with the elastic force. We also did the potential energy associated with the gravitational force. So those are the two conservative forces that we're going to run into the most. And so we should just talk about one other force that we're going to run into a lot, and that's going to be friction force. So to do that, noting that friction force is non-conservative, we need to talk about thermal energy. So thermal energy is generated when non-conservative forces like kinetic friction do work. I'm abbreviating, by the way. Non-conservative, I should say internal forces. So the classic example is internal friction, either or internal kinetic friction. So, and by the way, static friction generally doesn't do work because static friction generally, I mean, it can, but it doesn't often actually result in motion. Sometimes it can, but not most of the time. So let's look at an example that I like quite a lot. So let's say that we have a perfectly smooth, frictionless table, and we have two books on said table, and the books have very rough surfaces. Well, one book's on the table, and then the other book is flung at the first book horizontally. So you have book A and you have book B. So book A, and by the way, we're going to assume that you're able to launch this perfectly. So book A starts with some initial velocity to the right. This is the books before contact. And then it's going to move onto the right and then make contact with the books, with book B. So then at a later time, book A slides on top of book B. They make contact and they rub against each other. And so book A ends up pushing book B along and book B ends up slowing A down. So we can see here that this will produce thermal energy. And so these will end up traveling at some same speed together, call it VF, right? So just for the sake of analysis, just for the sake of our computational uses, let's just label some distances. So we will call the distance, I did it again. How did that happen? B, A, there we go. Okay, so the distance that book B moves, let's call that delta XB. And the distance that book A moves, which is going to be a further distance, remember, because it's starting off not on top of book B. That's the distance that book A moves. Yeah, I'm just, life's hard, okay? So those are just some labels, just so that we can understand the problem. So if we only consider the system to be book A, then the work that the friction force does on book A is negative. And the way you can see this is by using the work energy theorem, right? Book A is going to slow down a little bit. So that means that that means that the kinetic energy decreases, i.e. delta KE is negative. And so if delta KE is negative, then the external work applied to book A should be negative. Similarly, if the system is book B, then the work from friction is positive. And the reason for that is because the book B starts out at rest and ends up moving. And so the change in kinetic energy is positive. You have a positive number minus 0. And so the external work done on book B is positive. But what if the system is book A and B? Well, in that case, the friction force becomes internal. So instead of talking about the work done, we would talk about the change in thermal energy. So, but we can still try to figure out what the total work or what the total change in energy is of the system by asking about the work done on book A, the work done on book B, and then adding them together. So the work done on book A In this case, it's by book B, but it's an internal force, so it's just, so this will be a contribution to the thermal energy. This is minus F delta XA. The reason it's minus F delta XA is because the friction force pushes to the left because the book A is slowing down, but the distance over which that force is applied is this entire distance, because it's applied for the entire time that they are moving relative to each other, and that happens for all of delta XA. The work done on book B, on the other hand, would be F, because it's to the right and the book is moving to the right, times delta XB. So the force applied on book B is applied over a shorter distance because book B travels less far, even though it's the same force from Newton's third law. So these F's are just the magnitudes of the friction forces, and they're equal and opposite because of Newton's third law. So that means that the work done on both books, so this is like the total internal work done by the friction force, is therefore F delta XB minus F delta XA, or it's minus F delta XA minus delta XB. Now this distance here, that is the total distance that book A slides on top of book B. So it's like the relative change in position. So like that's the distance that, so book A initially starts off at one end of book B, and then it covers some extra distance. And that extra distance is the difference of those two deltas. And in particular, that difference in deltas is positive. And so what we find is that the work done by both, or the work done on both books, which is equal to the negative, well, the work done on both books, like the internal work done on both books, is negative F times delta X, say, sliding, which is the distance that book A slid on top of book B. And this is less than 0. And the reason it's less than 0 is because book A slid some positive distance across book B. And so this is positive. We multiply by negative F, and so you get negative, a negative work done. And then, so because this is an internal force, because all of these forces are internal to the book A plus B system, why was work done on book A negative? Because it slows down, right? A starts off at some speed, and then it rubs in contact with book B. The friction force opposes that rubbing, and so it slows down a bit. So because the system is A plus B, the work done on both books is internal. And so we can actually group it into thermal energy. And there's no external friction or anything. Yeah, the friction force here, you have friction this way and you have friction this way. Hopefully that helps. The work done, the total work done on the books is internal work. And so that means that we have the change in E thermal is equal to negative both books, which is just F delta X sliding. So then the work energy theorem becomes, because there's no external forces at all, the work energy theorem says, this is a continuation from what we did last time, that 0, because there's no external works, equals the change in kinetic energy. There's no conservative forces here either, plus the change in thermal energy. And so because the work done on both books was negative, the work done, or the change in thermal energy, is positive. Okay, so what does that mean if we use the work energy theorem? That means that the change in kinetic energy is negative. Which is to say that the total, even though book B speeds up, book A slows down sufficiently much that the total kinetic energy at the end of the day, once they're moving together, is less than just the kinetic energy of the first book. This is just to say that the friction force, even though it was internal, sapped kinetic energy from the system. Like it took kinetic energy away and converted it to thermal energy, and it can't be converted back. Now, the question then is, where did that kinetic energy go? Well, it went to thermal energy, and as you can possibly guess from the name, yeah, this is comparable to an inelastic collision. As you can guess from the name, that thermal energy, or that kinetic energy, went to basically increasing the temperature of the books, right? The books slid across each other, and you guys probably know from like sandpaper or whatever that when you rub two things across each other a lot, actually, just with your hands, right? Your hands are going to heat up. Because the change in thermal energy is the negative of the work done. Like this equation is how we get that. Right. So there's a discussion on why you can't kind of get back thermal energy. In the LibreText, I'm not going to spend a whole lot of time on it because it relies on a microscopic understanding of what thermal energy is. But I do suggest that you guys go take a look at that. It's interesting, and it'll perhaps make some things make a little bit more sense as to why you can't get thermal energy back. But for now, we're actually going to continue to talk about force and how it relates to potential energies. Right. So as we've already established last time, when conservative forces are involved and there are no non-conservative forces, we don't really need to compute work done directly. Like we had to compute the work done directly in this case with the friction on the books, right? Because when I wrote this is secretly, I did some line integrals in my head because they were easy. But when it's just conservative functions, you don't need to compute work in order to apply the work energy theorem. All you have to know is you have to know the potential energies, i.e. if you know the potential energy function for gravity, say like mgy plus u naught, then you don't actually need to go and compute the work done by a line integral. You can just apply the work energy theorem with just the potential energy function and you're golden. So it's actually really useful to work with this notion of potential energies rather than integrating forces. This is kind of the definition. That's the definition. So the change in thermal energy is defined to be the negative total non-conservative work, the negative internal total non-conservative work. So you take all of the internal works, you split them up into conservative and non-conservative. Then the non-conservative internal works, the negative of those is the change in thermal energy. That's definition. That's the definition of thermal energy. Anyway, so what I was saying is that it's useful to just use potential energies and just work with those. And then as long as you're working with conservative forces, you never have to worry about doing an integral again. Now that's great, but sometimes the work is sometimes computing the work with a line integral means that you can solve backwards for the force if for example you know the work. So the question is how do you figure out what the force is given a potential energy? I.e., what is the relationship between force and potential energy? That would be a useful thing to know if we're never going to do a line integral again. So we can just get potential energy directly from force or vice versa. So what we're going to do is we're going to consider a small amount of work done on an object by a conservative force. Small amount of work, we're going to call that small amount of work dW. Done internally on an object by a conservative force. And we're just going to play around with the equations until we get something out. Am I reacting? Yes. What? Oh, yeah, sorry. Yeah, so the small amount of work, dW, well, we know that the way you find the total work is by integrating a bunch of small amounts of work. And we know how to integrate a bunch of small amounts of work. It's just you integrate f dot dl. So a small amount of work should be equal, a small amount of work done by an internal conservative force, this force f, should be equal to that force dotted into that path length vector dl. So we can rewrite this as f sub x in the I hat direction plus f sub y in the j hat direction plus f sub z in the k hat direction. And then we just need to write down what is a generic path, small path. And that's fairly easy. It's dx I hat plus dy j hat plus dz k hat. And if you know, if you perchance know what the path is, then you could write dy in terms of like dy dx dx. But in general, this is fine. This just tells you that it moves a little bit in the x direction, and then it moves a different little bit in the y direction, and a third little bit in the z direction. And those could be 0 or they could not be 0. They could be whatever. And so we can do this dot product. It's f sub x dx plus f sub y dy plus f sub z dz. It's just the normal dot product. So if the force is internal, like we've already assumed, then, so let me write, because F is internal, we can write that the change in potential energy, or a small change in potential energy, dPe, well, by definition, it's the negative of the small amount of work done. And so this would be equal to negative f sub x dx minus f sub y dy minus f sub z dz. I just multiplied this whole thing through by a negative sign. Okay. So now we're just going to look at a special case. Suppose, for example, and we'll see how this generalizes in a minute, that the force is really just in the x direction, i.e. it doesn't point in the y direction, it doesn't point in the z direction, it only points in the x direction. And by the way, we're not assuming that these are constant, just that it only points in one direction. Then, if we make that assumption, it's the case that f sub x dx is equal to negative dp e, a negative small change in potential energy. Basically, dy and f sub y and f sub z would both be 0, so you would just be left with this equals this. And so then I just rearranged. I moved the minus sign over. And so we could rearrange this equation, and we end up with that the force in the x direction is the negative derivative of the potential energy function with respect to x. Now, just to make notation easier, so I'm not carrying around a PE everywhere, just keep in mind that we're going to change notations. So we are going to use the variable capital U for potential energy from now on. So instead of seeing PE sub g, I'll write U sub g, for example. And then I'll write, instead of seeing PE sub g as a function of height, you'll see U sub g as a function of height, right? That's all I'm doing. Right, so dPe is a small change in potential energy, right? It's just the change of potential energy, but a really, really small amount. It's infinitesimal change. Okay, so this tells us what the force is in the event that the potential energy, or that the force is only in the x direction. But what if the force isn't only in the x direction? What if f sub y and f sub z are not equal to 0? What if it has components in the x, y, and z directions? Well, we can still extract the x component by just treat the coordinates y and z as if they are constants, or as if they were constant. Potential energy is always the negative of work done by an internal conservative force. Yes. So what we're doing is we're trying to measure, in some sense, we're trying to measure what the force is given some potential energy, or vice versa, or try to, yeah. So, we're trying to figure out what the potential energy does given the force. So if you have a force in the x, y, and z direction, what you can do is you can just say, okay, what does the potential energy do if you just move it only in the x, if you only let the force act in the x direction? Okay, that will give you this negative dPe dx. And so that would be treating y and z as if it's not moving, as if it's constant. Imagine an object is on a track and it can't move in the y and z direction. It can only move in the x direction. In that case, the force would cause a change in potential energy given by this relationship. Similarly, you could do the same thing for y and z. Treat x and z as constant, put your object in a track so that it can't move in the X and Z direction, it can only move in the Y direction. And then again, you could do this same procedure to figure out how the force affects the potential energy in the vertical direction, and so on. So when we do this, dy equals 0 and dz equals 0, this is treating y and z as constants, i.e. y doesn't change at all and z doesn't change at all when we do that. And so what we end up with getting, or what we end up getting, is that the force in the x direction is still the same that we had before, but we write it a little bit differently. We write it with these curly d's. Now, some of you may have taken this far in calculus, some of you may have not, and so these curly d's rather than the straight d's have a special meaning. So when I write du dx with their curly d's, this means the following statement. It means take the derivative with respect to x treating y and z as if they were constant. So this just has the property, if u is, say, x times y times z, and then you wanted to do this thing, it's called a partial derivative with respect to x. The partial derivative of x times y times z with respect to x would just be y times z, because you treat the y and z as if they're just constant numbers. And then it would just be like 5 times x, the derivative would be 5. In this case, y times z times x, the derivative would be y times z. And so in general, we could do this for the y direction and for the z direction. We can see that the force in the y direction is the negative partial derivative with respect to y of u, and the force in the z direction is the negative partial derivative of u with respect to z. And so here, partial derivative with respect to y means treat x and z as if they were constant. And partial derivative with respect to z means treat x and y as if they were constant. It just means hold everything else constant except the variable you're differentiating with respect to. And so what this means is we can find what all three components of the forces are by taking partial derivatives. The end result then is the following. We get that the force vector, because the force is a vector, is the negative partial derivative of u with respect to x in the I hat direction, minus the partial derivative of u with respect to y in the j hat direction, minus the partial derivative of u with respect to z in the k hat direction. And so if you know the potential energy function u as a function of x, y, and z, and it could be some random scary function, then you can find the force by taking derivatives. And it kind of makes sense that you can find the force by taking derivatives, because we know that the way you get potential energy is by integrating the force. It's a negative integral of the force, because the work is an integral of force, and the potential energy is the negative of the work. So to undo that, to get the force back from the potential energy, it makes sense that there will A, be a negative sign, because the work is related to the integral and the work is the negative of the potential energy. And B, that you'd have to undo the integral, which is by taking a derivative. So just as a quick notational thing, this notion can be captured much more succinctly, written as this way: negative upside down triangle u. Now this upside down triangle has a name. It is a differential operator, and it means the following: I hat d by dx plus j hat d by dy plus k hat d by dz. And then you just let it act on the stuff or on u. So it would just distribute across, and it would work exactly as you might expect. This thing is called the gradient, and it takes functions and spits out vectors. And it's a really useful notion, and you'll probably hear about it if you're doing any sort of machine learning anything. And you'll hear about it a lot anyway in 9C. So just as a quick aside, this way of getting the force from a potential energy function, u, it only works for conservative functions, right? Because non-conservative functions don't have potential energy. Sorry, non-conservative forces don't have potential energies. So what we can actually do is we can give another way of figuring out if a function if a force is conservative. That is, a force is conservative if and only if it can be expressed as the negative gradient of a potential energy function. So, put another way, if a force has a potential energy function, i.e., if you can find some function u that has this property that if you take the derivatives with respect to the various coordinates and then you put the appropriate unit vectors and so on there, that you get back the force that you're interested in, then automatically that force is conservative. And similarly, or I guess conversely, if you're given a force and there is absolutely no way that you can come up with a potential energy function for that force that satisfies this criteria, then that force is not conservative. So there's a few examples that I mentioned in the lecture notes, but I'm just going to keep flying on by. So what we're going to do is we're going to test this notion of conservative forces, or test this formula for potential energies, or this formula on potential energies to get force for forces that we already know, just to make sure that it checks out. So let's do a quick test on, say, gravity. Let's use the gravitational potential energy and see what we get for the force. So for gravity, we're going to assume the standard coordinate system. We have x and y being up. And so in this coordinate system, the potential energy function for gravity as a function of x, y, and z would be mgy. At least that's the standard one. Remember, I can add a u-naught, and I'll show you how that works out in a minute. So let's just see if it works. Let's see what force we get when we take the gradient of this function. Why do non-conservative forces not have? Non-conservative forces do not have potential energy because it's not a well-defined notion. And like potential energy is actually defined by this equation, in fact. So if there is no solution to that equation, i.e. if there is no potential energy that exists that gives you the force back, then it cannot have a potential, then that force doesn't have a potential energy. Right, so the force then, in this case, the force due to gravity on an object of mass m, of course, would be negative partial derivative with respect to x of mgy in the I hat direction minus the partial derivative with respect to y of mgy in the j hat direction minus the partial derivative with respect to z of mgy in the k hat direction. Okay, so let's just do these derivatives. So what is the partial derivative of mgy with respect to x? Well, the partial derivative means you treat y and z with respect, or the partial derivative with respect to x means you treat y and z as if they were constants. And we know the derivative of anything, or the derivative of any constant, is always 0. So this term is 0 automatically. Let's skip over to z, because y is going to be interesting. Similarly, treating y as if it's a constant, the derivative of this thing, this is just a number now, with respect to z, is also 0. Now let's look at this last term. Now we just treat x and y as if they were constants, and then we take the derivative with respect to y. Sorry, x and z as if they were constant, and then we take the derivative with respect to y. In this case, there is no x and z, so we don't have to worry about that. And then we just take the derivative with respect to y as we normally do. So we get minus, what's the derivative of mgy with respect to y? It's just mg in the j hat direction. And this is precisely the force that we expect for gravity. It should be downwards in the y direction, and it should have magnitude mg, and this checks out. Now, just as a quick note, we could have equally well used a different potential energy function, which is the potential energy function that I gave above plus a constant. Remember, you're always allowed to do that, plus u-naught. And so, because g is just a number, you can factor a minus sign. This is the potential energy function that we came up with last time. So the reason why this would have worked equally well to get us the force is because the derivative of a constant is always 0. So once you start plugging in, once you start evaluating partial derivatives, this term never plays a role. It will not affect the term that's the partial derivative with respect to x because it's still 0. It will not affect the term that is the partial derivative with respect to z, because that's still 0. And the partial derivative with respect to y, well, this is just like ay plus b. And the derivative of that with respect to y is just a. It doesn't care about what b is. It doesn't care about the constant. So that's why you can always add a constant to a potential energy function, because the potential energy function, we only care about it so far as it gets us the force, because you can't observe the potential energy. It's like you can't say, aha, the potential energy there is 8. No, all you can say is either A, how the potential energy changes, in which case this constant doesn't matter, or B, you could ask what is the force associated with that potential energy, and you can measure that. In that case, the constant doesn't actually matter, because a derivative is just a very small change divided by a distance. It's not actually the initial potential energy. It's just some constant that you can add. You can always choose to add just some whatever constant you want. Sometimes it might be the initial potential energy, but it doesn't have to be. All right, let's do the same thing for a spring. Let's test out our method on a spring. So suppose a spring is displaced horizontally in the horizontal direction. It's displaced in the plus x direction. So the potential energy, so the picture here is like, you have your spring attached to a wall and you have a mass and you want to know the potential energy as a function of x, right? So the elastic force, the elastic potential energy as a function of x, y, and z, well, it's not going to depend on y and z, because it's only changing the x direction. We're not, like, the object isn't moving in the vertical direction. This would just be 1/2 times k times x minus x naught, where x naught, remember, is, say, the equilibrium position, squared. Okay, now let's find what the force is. The force is negative partial with respect to x, 1/2 k x minus x naught squared, I hat, minus partial with respect to y of 1/2 k x minus x naught squared, j hat, minus partial with respect to z of 1/2 k x minus x naught squared, k hat. So right away, you guys should see that there's no y in this term. So the derivative here goes to 0, because it's just like taking the derivative of. And so now we just. It'll be recorded if it. So let's. All right, okay, I'm back. Sorry about that. Hopefully you guys are all back too. Okay, good. The room never closed. Okay, excellent. All right, so all I did was I just said, okay, we can just take the derivative of this last term. And so that's just a normal derivative. And what you end up with is you end up with minus k times x minus x naught. And that's precisely what we expect the force to, or in the I hat direction. That's exactly what we expect the force to do, because we expect the force. Well, I mean, we know the formula. The formula is minus k x minus x naught. do, so our method seems to work. Last longer. All right. Normal, and this is a good check that that our method works for finding. Then you know that the force is non-conservative. If a force is non-conservative. I don't know why my internet's connected to the internet. Let me try calling in really quick. And then I'll turn off my audio.
Welcome to Zoom. Enter your meeting ID followed by #.
963-9197-5960 #.
Enter your participant ID followed by #. Otherwise, just press # to continue. You are in the meeting now. You are unmuted.
Can you guys hear me?
Can you guys hear me?
Testing 1 2 3.
1, 2,
Okay.
3. Okay.
All right. There we go. No more.
No more.
Okay.
Okay.
I'll just leave that there.
Leave that there. There should be.
Why is there an
Why
echo?
is there an echo?
Oh, because
my there we go. Sound is on place. All right. So how do we determine if a force is non-conservative? Hopefully, by the way, the first. This can be the x component. Testing 1. I'm on. Recorded properly, it'll be posted. Of the force. Potential energy function. That works for that component. Hello? All right, I'm going to keep going because it's being recorded. That's all I can do. Second
Mr.
step.
Booth,
Yep.
we can only hear like
Can you hear better?
every third or fourth word you say.
So I'm just going to keep going because it's being recorded, and I'm basically saying what I'm writing. So if you guys can see what I'm writing, then hopefully that's good.
Okay.
Is there any? It looks like it's registering my talking now. We good? We good? We good?
It sounds better now.
Looks like we're good. All right, excellent. Okay, let's proceed. I don't know why it must be Zoom because I'm on the phone, so it should be fine. Right. Step 2. Okay, so step 1, we know we have to try to undo a derivative. So we're going to integrate. Basically, we want to come up with a force. We want to come up with a potential energy that satisfies this. We want to try to come up with that potential energy. So given a force, what we're going to do is we're going to integrate it in just one of the components to try to find say, the potential energy function. And then we're going to test it against the other components to make sure it works. So after we integrate, we're going to just check that the candidate potential energy works for the other components. And the way we check that is just by taking the partial derivatives and seeing if they match with what we know they should be. So let me just do a real quick example. So let's ask the question or answer the question, is the force F equals AXY in the I hat direction conservative? So I'm going to, so first and foremost, because there's no K, this force is certainly not in the K direction, and it doesn't have any terms that are proportional to Z, we're just going to ignore the Z coordinate for now. We're just going to work in the XY plane. So we're going to try to find U of X and Y such that its gradient gives us this function, or this force. So step one, we write that AXY, we want AXY, which is the X component of the force, to be equal to the negative partial derivative with respect to X of some potential energy function U of X and Y. And so we can undo that partial derivative by integrating. So U of X and Y becomes an integral, and really this is an antiderivative of negative AXY dx. And so we can just do this antiderivative, and we end up with minus 1/2 AX squared Y. And here's the tricky bit, plus F of Y. So here we have to write F of Y because we're treating Y as if it's a constant. But the constant, or the constant that we get from anti-differentiating could depend on Y. We can't just assume that's the constant, because what if U of X and Y was like negative 1/2 AX squared Y plus sine of Y? Well, then the partial derivative would never actually see that. The partial derivative with respect to X wouldn't see that. And so we have to add this term that depends on Y, but it's constant with respect to X. So now we're going to test this function. Step 2, test on the other components. Now here you might say, what other components? But there's an important point. The Y component is 0. So we want that 0, which is the Y component, that should be equal to, or we're going to check if it's equal to, the negative partial derivative with respect to Y of the thing that we just found, minus 1/2 AX squared Y plus F of Y. So now we can just do this partial derivative. The first term looks like 1/2 AX squared. We're taking the partial derivative of this with respect to Y. So we treat X as if it's a constant. So this is just a number times Y. And then the derivative of that is just the number. We have an overall minus sign, so that cancels out. Oops. And then we have a partial derivative of a function that just depends on Y. So that's just a normal derivative. This is minus F prime of Y. And this is supposed to be equal to 0. But now look at this equation. We have a function that depends on Y has to always be equal to something that depends only on X. So there is no function F of Y that will make this equation always true. There is no function such that its derivative gives you something that depends on X, such that F of Y equals 1/2 AX squared. Like that's just true, right? Like if you have any function of X, or if you have any function of Y, like sine of Y, there's no derivative that you could take of that to give you something that depends on X. It's impossible. So because such a thing is impossible, this means that there is no conservative, or there's no function. There's no such function U of X and Y such that F is the negative gradient of U. Like there is not a function U that makes this true. And so that means that F is not conservative. So this is how we check. We check by assuming it is conservative, see what it would have to be conservative, and then getting a contradiction, getting that something like this has to be true, which is impossible. So there's another example that you guys should take a look at, and otherwise we'll move on. Let's talk very briefly about equipotential surfaces. How far are we supposed to get today? Ooh, rip. Okay. So equipotential surfaces are a really quick idea. They're They're useful, but it's just a way to visualize these things. So what I want you to imagine for equipotential surfaces is those old topographic maps where it shows like squiggle lines on the map, and those squiggle lines represent like different heights, right? So the map might look like this. You have like, and maybe it's like a mountain range, and you have something like this, and then you have like the peak of the mountain is inside, and then you have like a valley over here that represents different heights, and then you have like another hill. Maybe it's not very tall, so it only has a few lines. So in equipotential, this is an example of an equipotential surface, actually. This would be an example of an equipotential surface for gravitational, or This would be an example of equipotential lines for the gravitational force. So equipotential surfaces are only surfaces because this is a two-dimensional plot, or a two-dimensional graph, really. And we have to think one dimension up because potential energies live in 3 dimensions. On Earth, it's enough to just do 2 dimensions because, you know, basically how do I want to phrase this? The potential energy doesn't change if you move horizontally. But, you know, for some other random potential energy, it could change in different places. So the example to look at here is suppose we had some random potential energy function that was like u of x, y, and z let me put this down somewhere else, is equal to negative a, where a is just a number, times x squared plus y squared plus z squared, right? So just as a quick reminder, x squared plus y squared plus z squared, or rather the square root of this, is the distance from the origin of the coordinate system, the distance from the origin to the point x, y, z, right? So that means that this thing, a squared x, or x squared plus y squared plus z squared, is related. It's just the square of the distance, right? So given this potential energy function, every point in the x, y, z space that is equidistant from the origin Can you hear me? No, my phone just cut out for some reason. I don't know why it hung up, but my phone hung up, but I'm back, right? Right, so every point that is equidistant from the origin has the same potential energy. Because if it's equidistant from the origin, then that would mean that it has the same x squared plus y squared plus z squared value. And the potential energy is just proportional to x squared plus y squared plus z squared. So it'll give you the same potential energy. And so this is to say, and hopefully you guys remember your geometry, points that are the same distance from the origin represent the set of points on the surface of a sphere. So this says, with this potential energy function, every point that is on the surface of a sphere has the same potential energy. And so what we can do is we can draw shells around the origin and every point on each of those shells has the same potential energy. And these are surfaces, right? And that's why they're called equipotential surfaces. Every point on those shells has the same, i.e. potential energy. So this is the notion that it's like a 3-dimensional version of a topographic map, right? You have like a bunch of surfaces and every point on that surface has the same potential energy. So then the question is what is the force in this case? Well, the force in this case, we can find it relatively easily, but I'm not going to bore you with all the details. The force, by taking the negative gradient, would give us 2 alpha times xi hat plus yj hat plus zk hat. That just is the force. You can go and check it for yourself if you want to. But note that this vector points from the origin to the point xyz. So for example, it would point like here. The vector would be like this vector if it points at a point xyz. So it points precisely from the origin to the point xyz. And so what we find is that F, in this case, is perpendicular to the spheres. And the spheres being the equipotential surfaces. So there's a general result that we can find here, and I'm almost done, and then we'll call it a day. The general result is that a conservative force always points perpendicular to its equipotential surfaces. In particular, it points, or they point, from greater potential to lower potential. So this is just generally true. And we can see this in this example. We see that the force points directly to the point, and that would by definition be perpendicular to the surface or perpendicular to the sphere. And then we can also see that the direction it points in is away from the origin. And if we look at the potential energy far from the origin, the potential energy far from the origin is when, or rather the potential energy near the origin is when this quantity, x squared plus y squared plus z squared, is smaller, and the negative of that is a small negative number. And the force pointing away from the origin points towards further spheres, so it points from small values of x squared plus y squared plus z squared to large values of x squared plus y squared plus z squared. And so those are more negative because the x squared plus y squared plus z squared terms are greater. So it points from high potential energy, the inside or the inner spheres, to low potential energy, the outer spheres. And when I say high and low, I really mean like higher numbers are numbers that in this case, because they're negative, they're closer to 0. So like -2 is higher than -5, for example. So that takes us through to the end. We did not get to talk about potential energy or energy diagrams, and we will talk about that on Monday. So I'm going to end